Today we are beginning the chapter number 10, properties of fluid, mechanical properties of the fluid that we are going to discuss in this chapter. First question that comes in our mind is, what is fluid? Fluid is a substance that can flow easily. Liquids and gas are considered to be the fluid because they can flow. Okay, so they are all included in the fluid. Now the second question comes in our mind, but liquid and gases both are fluid. Now we have to distinguish between them, which property is common between them. See, liquid and gas both are fluid. The basic difference between them is that liquid is incompressible. It has fixed volume and free surface, while the gas is compressible. A gas which is filled in a particular container, then the volume of the gas will be equal to the volume of the container. Gas is not having any free surface, okay? That is the main difference, okay? Gas and liquid can easily flow. It is common fact, and they offer very little resistance to shear stress, okay? Now there is a difference between the liquid body and solid body. See, shear stress can change the shape of solid, keeping its volume fixed. Shape of fluid changes by application of very small shear stress. The shearing stress of fluid is about million times smaller than that of the solids. Okay. Now here fluid mechanics is studied in two different parts. One is fluid statics. Okay, we shall talk about the fluid statics and then we shall talk about the fluid dynamics. Now in the fluid statics, this is the branch of fluid mechanics. Okay, the forces and pressure acting on the stationary fluid are studied. Here the fluid is taken in a stationary state, while in fluid dynamics, in this branch of the fluid mechanics, motion of fluid and properties related to its result of force acting on the fluid are studied. Okay, so here the fluid is in motion. Okay, and motion of the fluid and properties related to it as a result of forces acting on the fluid are studied. Now the next part is definition of thrust and pressure. Okay, their unit dimensional formula. The force applied on the surface in the direction perpendicular to the surface is called the thrust. Due to thrust, liquid flow out from the whole of the container. Thrust is a force, okay, and its unit is Newton. Dimensional formula is m1 l1 t minus 2. Now pressure is force per unit area in the direction perpendicular to it is a pressure, or we can say force is nothing but force acting on a surface per unit area in a direction perpendicular to surface. Try to understand, force perpendicular to the surface is taken, and this force per unit area perpendicular to the surface is known as pressure. Pressure is F upon A. Its unit will be Newton per meter square or Pascal. Its CGS unit is dyne per centimeter square, and its dimensional formula is m1 l minus 1 t minus 2. Now is pressure a scalar or a vector? Pressure is a scalar quantity. Try to understand, because at a point fluid pressure is equal in all directions. This you will study, okay, in the further, in the future, rather in the proceeding way, in the proceeding different lectures. So it shows that no direction is needed to show the pressure, force upon area. Okay, it is the component of the force. Now this is very important, that when you want to find the pressure, then say for example force is acting in this particular direction on this surface, you have to consider the force which is perpendicular to the surface, so you have to take the component of the force which is perpendicular to the surface. Okay, so it is not the force itself, so the direction of this force is not considered. The component of the force has to be considered, and this component of the force which we have to take is in the direction perpendicular to the surface. Okay, and that is why again this component is not a vector quantity, so it is the component of the force normal to the area under consideration, and not the vector, that is force itself which is acting, is considered. Okay, so the pressure is a scalar physical quantity. Now the next topic is that we want to show that force exerted by rest fluid, or we can say fluid at rest, is perpendicular to its contact surface. Now see, when an object is submerged in the fluid at rest, the fluid exerts a force on its surface. This force is always perpendicular to the object's surface, because if there were a component of force parallel to the surface, the object will also exert a force on the fluid parallel to it. As a consequence, the Newton's third law, if parallel component is taken, try to understand, then what will happen, that parallel force, or we can say parallel component of the force, will have the other reactive force according to Newton's third law of motion, and these two forces are equal in magnitude and opposite in direction. So what will happen, they will cancel out each other's effect. So this force will cause the fluid to flow parallel to the surface since the fluid is at rest. Hence, the force exerted by the fluid at rest has to be perpendicular to the surface in contact with it. If there is a parallel force, then fluid will start flowing. Okay, when the object is submerged in it. Okay, but it is not flowing. If the parallel force is there, then the fluid must start flowing. But it is not flowing in the observation. It is found to be stationary. It means that that parallel component is not present. Only the perpendicular component or the fluid exerts the force perpendicularly on the object. So the force exerted by the liquid in the beaker on the submerged object or on the wall is always perpendicular to the surface at all points. So this object which is submerged is experiencing the force perpendicularly on the different wall, not in this particular direction. Try to understand, the force is not parallel to the surface of the submerged object, otherwise this fluid would start flowing, and it is not flowing in the beaker, it is stationary. It means that forces are perpendicular to the surfaces. Okay, now we talk about density. Density we have already discussed in some of the earlier chapter. Density is nothing but mass upon volume, or it is the ratio of mass to volume. It is denoted by rho. So rho is equal to mass upon volume. Mass is measured in kilogram. Volume is having its SI unit to be meter cube. So its unit is kilogram per meter cube. And CGS unit is gram per centimeter cube. And the dimensional formula is M1L minus 3 T0. Okay. Now we talk about the specific density. The relative density. The relative density of substance is the ratio of the density to the density of water at 4 degrees Celsius, or we can say density of substance upon density of water at 4 degrees Celsius temperature is a relative density or specific density. There is one example, density of aluminum is 2.7 into 10 raised to 3 kilogram per meter cube, and density of water at 4 degrees Celsius temperature is 10 raised to 3 kilogram per meter cube. So relative density will be 2.7, or we can say aluminum is 2.7 times heavier than the water, we can say. Okay, So this relative density gives an idea how a particular substance is heavier in comparison to the water having the same amount of volume. Okay. Now see, this is a very small example how the pressure is calculated. Force is exerted on the surface of 0.1 meter square area. So area is given 0.1 meter square. Okay, we want to find the pressure. Here force is applied is 10 Newton. Now see, we have to take the component of the force. Okay, now component of the force which is perpendicular to this surface is this is the component. Okay, and that component here the theta is 60 degree, so it will be 10 cos 60, so it becomes 10 into cos 60 is 1 by 2, so it becomes 5 Newton, which is force which is perpendicular to the surface. Now pressure is force upon area. You just don't have to take the 10 Newton force, you have to take the component of the force which is perpendicular to the surface. So it is 5 divided by 0.1, then that will be 50 Newton per meter square. Okay. Now we shall discuss and prove the Pascal's law. The law is the pressure in the fluid at rest is the same at all points. Now we want to show the proof. Now we consider A, B, C, D, E, F is an element of the interior of a fluid at rest. So this is the fluid element which is considered. Okay. Now this is a prism like right angle prism like element of the fluid which we are considering. Okay, these are different area. Here the area of this ACFD, area of ADFB, okay, and FBCE will be three different sections. Okay, so these are the three different sections. You can see EFCB. This is another section ADBE. Okay, and this is the last section. Okay, that is ADFC. Force acting here on this is FB. This is the force on this surface, that is FB. Here the area of ADCF, try to understand, area of ADCF is taken as area of this B surface, or we can say AB. Okay, then area of ADBE, this area is taken, area of ADBE is taken as area of C surface. Okay, and this surface is taken as surface A. Okay, and the area of this BEFC, area of BEFC is taken as area of A surface. So there are three different surfaces. This is surface B, this is surface A, and this is surface C. Okay, area of this surface is AB, area of this surface is AA, and area of this surface as AB. Now force here acting is on this surface is considered, okay, as force on B surface is FB. Okay, now we will find the component of this force. Okay, now try to understand this way. The triangle is shown. To understand it in a two-dimensional way. Okay, say for example, this is the particular surface, that is B surface, on which the force acting is FB. Now this force is in this direction, this angle is taken as theta. So here this particular angle will also be theta, and this FB force is in this direction, so FB cos theta force will be in this particular direction. And FB sin theta force, this will be the FB sin theta force, and that will be in this particular direction. So FB cos theta force is acting on surface A, try to understand, and on surface B, or rather surface C. It is a surface C. This surface is surface C. Okay, this surface is surface C. So this surface is surface C, and on surface C the force acting is FB sin theta. Try to understand. On surface B the force is FB. On surface A the force is FB cos theta, and on surface C the force is FB sin theta. Try to understand. Now we consider the area. Say for example, the area on which the force acting, that is, we consider this B as our, rather this B is taken, okay, this B is taken as the reference surface. This is the B surface, okay, this surface is B, okay. The area of this is AB. Try to understand. An area vector is always perpendicular to the surface. So this is the area vector AB of the B surface. Now here, as I have explained, this will make theta. So this will also make theta. They are vertically opposite angle. They are vertically opposite angle. Because they are vertically opposite angle, okay, this angle is theta, so this must be theta. So try to understand the component of the area AB in this particular direction will be AB cos theta, which is shown here. AB cos theta, and perpendicular to it, perpendicular to AB cos theta, that is this component will be AB sin theta, that is shown here. So area vector which we are considering, again, say for example, this is the area of B surface, which is AB, and here the angle which is made by this vector is theta, so this angle will also be theta. So component of this AB in this direction will be AB cos theta, and in this direction the component will be AB sin theta. So if you consider the area of this B surface, try to understand, area of this B surface, this area, if you consider as AB, then the area of this particular segment will be AB cos theta. Try to understand, because area, here this angle will be theta, and area vector is in this direction, so this will be AB cos theta. This will be AB cos theta. So this particular area will be AB cos theta, and this direction will have the component AB sin theta. So this area, this particular area will be equal to AB sin theta. So force and area for different surfaces are now with us. For this particular segment, or we can say this section of the considered triangular shape component or segment of the liquid, for this particular we have force FB and area AB. So force upon area will be FB upon AB, that is pressure on this segment, that is slanted segment, which is having the name ADFC, and ADFC is having the force FB and area AB, so pressure will be FB upon AB. Now for this particular segment, that is downward segment, the force is in this direction. Okay, so the force here, because this force is in this particular direction, so the component of the force in this direction will be, as this is theta, this will also be theta, and it will be FB cos theta. So force is FB cos theta, and as I have earlier explained, that the area of this particular segment, lower segment, this one, this segment is having the area which is nothing but AB cos theta, as I have explained here. So AB cos theta is the area of this smaller base, okay, this base here, and FB cos theta is the pressure, so FB cos theta is the force, so pressure will be FB cos theta upon AB cos theta, and that will be FB upon AB. Similarly, if you calculate for this, then here the force is FB sin theta. This FC force is nothing but FB sin theta. So force on this is FB sin theta, and area of this particular segment is AB sin theta. So pressure will be again FB upon AB. So pressure is same on each and every segment of this particular fluid section which we have considered. Okay, so all the forces and pressure are so divided so that you get the same pressure PB as FB upon AB, PA as also FB upon AB, and PC, that is pressure on C surface, is also FB upon AB. So we can say that the pressure in the fluid at rest is the same at all points, and hence the law is proved. Okay, so by taking the geometry and the figure into consideration and different components of area and force, we can easily show the law which is proved here, which is nothing but the pressure in the fluid at rest is the same at all points. Okay, thank you very much.